Welcome to Boston University summer term. First, I want to remind you that for this course, one of the requirements is using WebAssign. So if you haven't done it before, please pick up a page with the instructions and use it as soon as possible. My name is Valentin Viktorovich Voroshilov. Could you say it, please? Exactly. That's why I've changed it many times, until finally I left only one letter. That's going to be my signature. So when I'm going to communicate with you, if you see Mr. V, that's me, and that's how you should call me. That's my nickname for my students for many years. Simple, convenient, and no one else has it. I was born, grew up, got my education in Russia. So English is not my native language, as you can hear. And on top of that, I have no formal education in English. I learned it using books, tapes, videos, watching TV shows, Friends mostly, and well, simple language, everything clear. And so far, I haven't met a student for whom that would be a problem, especially in physics, right? A half of time I could speak Russian, that would make any difference. And I also have to manipulate with my muscles in a special way to sound clearly. So sometimes if I forget, I may think I speak English, but for you it might sound French. So what do you do in that situation? Yes? Raise your hand, yeah, and ask, Mr. V, what did you say? Sometimes I will answer, sometimes I will not, but at least it will give me some indication, right? This is a typical example of some statements from student evaluations from the past. As you can see, for every negative statement, there is a positive, and for every positive, there is opposite negative. And I like this one especially. You can tell he wants his students to understand and do well. He never felt like he cared for his students. So, two people for 6 weeks have been watching the same person, hearing the same words, and came up with completely opposite views. As a scientist, what would you conclude from this fact? That's a fact, experimental fact. So, how should we react to it? Anyone? Yes? That's too scientific. There's a simpler approach. Yes? Well, I've been doing it again and again, and as you can see, there is much more on web. Everybody now is on the internet. So you can find what other students might tell, and you have to make your mind in the future. Some people believe in the theory of multiple universes. So if you believe in that, I can assure you that if you, right now, taking the same course in a different universe, in that universe, your grade will be lower. In this universe, you get the highest grade possible. But that requires some work. First of all, I have to remind you, if you go to the official link, it gives you information about important days. You have time to make your mind. In the past, it's never happened that half of the class would just drop. One student, couple of students. It's natural, mostly because of family or health issues. But still, I have to point at this opportunity for you. If you hate it, don't stay here. You know, the most important thing for everybody is our health. So if we hate something to do too much, we get sick. So it doesn't worth it. Now, so final reminder, please create an account if you haven't done it yet. If you have any issues, you should see me after the lecture so we could fix any issues related to WebAssign, because right now I will ask you a question. But before, actually, I want to check if I see what you see. So this is my side of the WebAssign. So this is a standard, well, I wouldn't call it assignment, yeah. A standard set of questions. And I can see right now how many students actually logged in and answered the questions. See, there's a distribution. And I can see that 2 students have answered already question which hasn't been asked yet. Don't do that. You know, WebAssign is a very convenient tool because it collects all the information about every student, what and when was answered. So, okay, the 3rd question, and actually, okay, the 4th question. So at least 2 students right now doing what is a violation of the first page of the syllabus. That's called cheating. You can't answer a question which you don't know what the question is about yet, right? So if you try to go ahead and just randomly select any answers, that's cheating. And according to BU policy, that's punishable. So don't do it anymore, please. Well, let's go back. So I can see what is happening. You can see that I can see what is happening. And this is the question now. Question number 2, which you're supposed to start answering right now. It's about your personal attitude about yourself. If you think that you are terrible at physics, you can select the first number. Yeah. If you think you are very good at physics, 9, and anything in between. Now, you don't have to use your laptop because WebAssign, again, is a good platform. You can use your tablet or even a smartphone. You should try. So if you don't want to carry your tablet every time, you can find something smaller and lighter. And I got to refresh it. Please, I can't hear me, all right, too late. If you're late, it happens sometimes, and you're entering the room and you see something on a bench, on a table, you should pick it up first and then you should go. So, number 2, we can see a very wide distribution, which is a very natural, it's, you know, distribution. I haven't seen any deviation so far. But I want to tell you up front that the way you feel about yourself has no correlation with the final grade. It's not about feelings. It's about work. I ask this question only because it's interesting to see if your attitude would change in the end. And you would see it as well. But what do you need to do in order to get the best grade possible? Well, learning physics, learning in general, is like building a pyramid. If you want to build the top, first you need a solid base. We call it the background. And the only difference between many people in this room, in this world, is the background they have due to, well, many different circumstances: family, culture, economy. So if you have already all needed background, it's going to be easier for you to move through the course. How do you know if you don't have certain parts? Well, normally you can just see that for your friend, something is easier than for you. It might be mathematics, or might be some life experience with some things is missing. It's not a big deal, because for this course, we don't really need a very big knowledge of solid knowledge of mathematics, or life experience. So any missing background actually is relatively easily recoverable, can be recovered. And I strongly recommend do that, because otherwise, if you're still missing some background, your final building, final top, might not be full. And as you know, you're not required to take any physics courses before taking this one. But also, there is no restriction on people who've taken that before. I can't ask, okay, have you taken physics before? Yes, well, go away. No. So there is some difference in people's background, and that's natural. That only might affect the amount of time or effort different people may need to put to get the same final result. The result, the finish line, is the same for everyone. It's achievable for everyone. In theory, everyone can get an A. In practice, that's never happened before, but who knows? Maybe you will be the first. Now, there is a reason, at least one, among many reasons why you're taking this course here at BU, not at Harvard or MIT or UMass or Bridgewater State University or ITT Technical or Wentworth or anybody else. So I don't know that reason. I don't care. What you should know is Boston University is one of the top research universities in the world. So we, as faculty and administration, have certain expectations about students taking these courses. And those expectations are mostly about your ability to plan ahead, to be organized. Don't wait until the deadline is looming, Be on time, do a little bit every day instead of waiting until the last minute, and you will be all set. That's a standard expectation. So please check the syllabus. That's just a copy. This schedule helps you to plan ahead, so you know exactly when and what we're going to talk about. Of course, in reality, slight deviations are possible, but only slight ones. This is a very intense course. The difference between this course and any similar course in the spring or in the fall, which BU also offers, is that in 6 weeks, you have to learn the same amount of material and do the same amount of work people do in 13 weeks or 14 weeks. So I usually recommend, well, let's say you don't work. I know that some of you actually work. So if you don't work, I wouldn't recommend taking too intense courses in the summer, like physics and chemistry, or physics and mathematics, or chemistry and mathematics. It might be too hard. If you do work and your hours are considerable, 10 hours a week, in that case, you should figure out how you balance that time, because everybody also has to sleep and eat, right? And party, no? These are exams. I strongly recommend do the exams on these days. The only exception usually is, well, car breaks or leg breaks. In that case, you should notify me as soon as possible. Exams. Well, a standard exam is composed of 8 problems. Those problems are similar to problems we will be solving together here in this room, or you will be doing on your own, or with your friends, or with teaching fellows when doing homework, or doing the lab exercises. The key word is similar, so it's not identical. So memorizing the solutions for all these problems will not help on its own. More importantly, to be able to recognize the similarity between the problem we need to solve now and the problem we've solved in the past. And that is the most important practice, recognizing similarities and differences between, well, people, jobs, problems. And to do that, you should practice. Practice doesn't make perfect, but practice makes things better. To practice, you can solve problems, bless you, from the past. They're available on Blackboard. You should check if you have the access. If you're a BU student, you should be all set automatically. But if you are from outside, you may need to talk to IT people beforehand to make sure you have the access to Blackboard. You have access to videos, because this, well, I requested this to be captured on the video. Only in an hour I will learn if that actually happened. And what will be the quality of that. Sometimes we need to fiddle with things. So practice homework is available on the website. It says practice homework. So practice means you don't have to do anything from that. But you can use it as an additional source for your work, getting kind of intuition on clusters of problems which should be solved using similar approaches. And we're going to practice here, of course. And after the lecture, you can use all those sources, videos, your notes. During the lecture, your most important part is fixing what might not have been clear enough, so you could clear it up later. So there's an impression, especially in the US, that every student at every lecture should get complete understanding on every single point of that lecture. If you just say this sentence, you understand that's impossible. So I try to best of my abilities, to aim my material at like 60% of the audience, and for 60% of the audience, at least 80% of all I say should be clear. But of course, for some people, it might be too easy, and some people might find it too challenging. If you find it too easy, don't get cocky. It gets harder later. If you find it too challenging, that only means don't wait until, day after tomorrow. Right after the lecture, if you have time, go to office hour, or send an email, or post a question on Piazza. So everything which might not be clear during the lecture should be as clear as possible, as fast as possible after the lecture. And of course, anytime when you want to ask a question, you should ask a question. That's your job. And depending on the question, Sometimes I immediately give an answer if the question is directly relative to what we talk about. But sometimes the question might be coming from something very far away. In that case, I usually point at what should be reviewed, and we can talk again later in office hours. Officially, BU allows you to miss something, some lectures if you feel sick or something happens, family issue. But from my experience, missing 5 lectures is basically missing a whole week, which is 1/6 of the course, and usually that affects the grade. 1 or 2, that usually is fine. So I don't recommend missing too many lectures, even if that's allowed. Labs. So as you know, officially we have to do the first lab today. I've seen that some of you have it done already because it's been available. It's not actually a lab per se. It's an online exercise which has 3 different parts, 1 short, 2 long, and you have all day to finish it. You can do it now, right after the lecture, during your lab time, after your lab time, before your lab time. You can do it here, you can do it at home. It doesn't matter. It's open until 10 p.m. And if something happened to your computer, you can go to that room, 134, our general lab room, and use computers in there. This is the schematics for rooms. So if you leave this auditorium through this door, so this is what you're going to see right in front of you. Sometimes we may need to use that room 134. On your right will be 128. On your left will be 134. And the undergraduate resource room, where all office hours take place, is on the right from this cabinet. Many labs require using computer software, and I just ask you 2 things. First, don't install anything on those computers. Or if you even asked, just ignore it, just cancel it. We have staff member who takes care of everything. And the second thing is, see, this is a picture of a lab just before the lab started. See how everything is clean and shiny. So standard professional ethics requires leaving your working place after you in the same condition. You've got it. So try to, just before you finish your lab exercises and you're free to go, clean it up a little, because it's going to be messy. You're going to be writing, erasing, moving stuff. But before that, before you go out, just leave it clean. And of course, please be aware of your surroundings. Don't poke anybody in an eye. If you use a laser pointer and you will, don't point it at anybody. Don't drop heavy things on your partner's food, you know. So be careful. Safety is the #1 issue. Homework. So the homework one has, well, every homework has 4 parts, depending on material we are talking about. And this is the recommended timeline for the homework #1. Homework 1, part 1 is already available, and I would recommend start working on it. So this is a recommendation. Yeah. I also would recommend to check what professionals in education write about homework assignments, how much homework usually on average, how much time it takes. And from the past, I cannot predict how much time would every student need. Some people do it in 1 hour. Some people may need 3 hours to finish 2 or 3 problems. So you should start as soon as possible and get the feeling how much time you may need to, move along, so you could plan accordingly your work. All homework assignments are on website. We will not have any printed homework assignments. Everything is on a website, which is good, I think. Number 4 is your magic number. First of all, you have 6 trials for every part of every problem. And you can use them independently. And if that is not the case, you should notify me immediately. Maybe something with settings might have gone wrong. But if you've tried to solve a problem and even after your 4th trial it still is wrong, stop and use the left 2 trials to finish this problem with the teaching fellow. Come to office hours. Now, usually you are safe if you keep 4 digits after the decimal point. Your answer considered correct if it close to the answer in the website. And close means the deviation shouldn't be more than 4%. That also gives a clue. This is an example when a student basically wasted 2 trials, because the submission number 4 was wrong. What is 4% of 277? Well, it's about 20-something, 2 something, right? 4 times 400, 400 close to 500, 500 divided by 250, 2. So the correct answer should be larger by 2, which gives 279-ish, or less by 2, which gives 275-ish. So this answer just cannot be correct. So if this answer was wrong, trying this answer is losing a trial, or this one. So this is how many office hours we have. Plus, if it's Monday and we have a lab on Monday, there will be additional office hours from 6 to 9:20. Or if it is Wednesday and we have a lab on Wednesday, again, additional office hours will be offered. All this information is available on Blackboard, and also on the left by the undergraduate resource room, there is a large wall stand, and just a copy of the syllabus with a copy of this is already posted. Grading. Well, the total grade based on the scale. Lectures, investigative laboratories, just labs, homework, and 3 exams. And when the total grade is calculated, of course, we have a distribution of numbers, and that distribution of numbers should be split in smaller pockets. One pocket is for A, another for A minus, etc., etc. You know that. But what we should understand that when we divide a continuous distribution into separate intervals, we always have boundaries. There will be a boundary between A minus and A. It's inevitable. There will be a boundary between B plus and A minus. It's inevitable. It means there always will be someone close to a boundary. This is a standard average scale. Again, I copy from the syllabus. But in reality, those boundaries slightly, well, not every time, but might be slightly shifted up or down. This is one example from the past. And how do we set the boundary? And we, I don't mean me, I mean university, because there is a procedure. The boundary has to be stable. That's it. That's the most important feature of the boundary. It has to be close to, well, that projected boundary. But if you look at the grades, this is an example again from the past, you can see that, for example, the gap between these two grades is very small. The gap between these two grades is also very small, but the gap between these two grades is a half of a point. That makes this boundary stable. Stable to what? Well, errors, rounding out. So as long as this big gap is found, the boundary is drawn, and it can't be changed anymore. So teaching is a combination of science and art. Grading can be done by a computer. It has a very straightforward procedure and should be done by a computer actually, but people are just too lazy to write this software. Now here, a copy of an actual email from a student. Would you please round my grade? What do you think? What was the answer? No? See? Again, this is an actual copy of data from the one of the, I think it was 2013 marathon race. What would happen if we would round up all numbers? We wouldn't be able to see the distribution. We wouldn't be able to align people, and we wouldn't be able to draw boundaries. So rounding up is not an option. Now, I feel I put some effort, so please move my grade up. Well, again, this is the equation for the total grade. It has, again, these 6 components: lectures, labs, homework, exam, exam, exam. There is no term which says effort. There is no term which says, well, anything else. And maybe it should, but it's not up to me. It's not up to anybody else. This is the equation. That's it. So there is no option to just physically move it up, as well as do something extra. Again, there is nothing extra in this equation. Plus, this email has been sent, well, you see, after the final grade has been calculated, which means the semester officially was already over. So the best strategy is just not losing any points. Lectures, if you hear, automatically gives you 7% of your total grade, automatically, even if you're just sleeping and just waking up when I ask a question and enter something in the WebAssign. If you're in a WebAssign and you did it right, you're automatically all set with the lecture. Labs, all you have to do, just go and do it. 2 teaching fellows will be helping you around, and trust me, you will finish it on time with the total grade, unless, again, you're sleeping somewhere else. Homework, again, that only depends on your planning skills. Just don't wait until the deadline. Do as much as you can, immediately as you can. So that gives you 37% of your total grade automatically, without practically any extra work. Exams. Well, if you really put your effort in these 3 parts and you did it on your own, well, maybe with the help of your friend or a teaching fellow or tutor, doesn't matter. But if you get a clear understanding of everything you've done, of every step, that's it. Your exam grade just cannot be low. It's impossible. That's a law. Well, okay. This is what I want to ask you now, question 3. So we go back to the web assign. Physics is, please select one word, one answer, which you think fits the best. And I'm going to switch so I could see. So you should now choose the number and remember it. Okay? Remember your number. Now I'm going to resend. Well, while doing this, again, just last glimpse. This is the question number 3. So this is a distribution. And again, it is very, very common. The most popular answer is 8, which is hard. Well, I know you may think so, but you're wrong. If you think physics is hard, it's only because someone lied to you. And I'm not going to lie to you. It's not hard. It has a very clear logic. And as long as we start seeing that logic, you can solve any problem, not just in physics, but in any other subject, even in life. And keep in mind that there are things which might be more complicated than learning how to solve problems. Yeah? For example, learning how to walk a rope is much harder than learning how to calculate forces in this situation. Physics is based on imagination, some mathematics, and constant work, constant trial and error. Constant trial and error. Why do we need imagination? Well, physics based on experiments. And over hundreds of years, thousands of experiments have been used to build up the building of physics as a science. We cannot do all possible experiments. So very often, we just have to imagine what is happening. If we can clearly imagine what is happening, the name for that is a thought experiment. Well said. But of course, we should help ourselves by talking out, drawing pictures. Mathematics, yeah, kind of important. And to help you to see your weaknesses, you should do this. It's not a test, it's a self-test. So you do it. I will post answers probably tomorrow. And every time when you felt confused, you should write a note, go to office hour, talk it out. Because every single calculation presented in that test eventually will be used in this course. But not today. Yeah. Again, it's not actual law of learning, but based on my experience, everybody who can memorize multiplication table, can solve quadratic equation, and knows how to solve right triangle, mathematically should be all set. That's that's minimum, which we're going to be using very often. The rest is just once in a while. Oh, and adding fractions. Well, everybody makes mistakes, especially when we learn. Yeah? When a baby learns how to walk, he or she falls, stands up, falls, stands up. So that's what we call trial and error. You have to try until you try and make a mistake. You actually can't learn. I can't learn. Nobody can't learn. Mistakes are inevitable. unavoidable, and that's only how people learn from mistakes. Everything what you hear now is a quasi or pseudo learning. And of course, it helps to have a group, of friends, fellow students to talk it out. So collaboration, face-to-face or using Piazza is usually helpful. Physics is science. Every science is based on observations. So we see something. We may not know what we see, but we see it, right? And we see that something is happening to that thing we see. So when we look around, we see things. Well, we call them objects. Yeah. Thing. And you see, if I take this thing, and this thing has this thing, and if I do something to this thing, and I make it like this, and then I take this thing, and I take it out, and then I put it in this thing, and then I do this thing does that thing. What is wrong with what I just said? What is wrong? Yep. Clarity. First of all, if you would read this sentence without actually looking, you wouldn't understand a thing. But any science, every science is based and is built on communication. So to do that, every science has developed its own language. We don't call it thing, we call it projectile or launcher or ball. And it's just not moving, it's flying, and it travels through certain trajectory, and there are many, many other things we have to talk about. So the most fundamental part of learning science, including physics, is learning this language. And this language also includes descriptions of what? Properties of those objects, like what is a property of this object?
Yellow.
Yellow. What else?
Spherical.
Spherical. Or round. What else? What else?
I would assume bouncy.
Might be, yeah. And we can keep going. Even for a simple object like this ball, we can list many, many properties. For example, it might be very valuable for me. It used to be a gift from, yeah. Or it might be very expensive or very cheap, hot, cold, etc. It might have a charge. So for every object, we should have in our mind, in our memory, a list of possible properties, but only some of those properties are important depending on what's happening. And what's happening, that's what we call a process. For example, this we call a motion. What is the property of this motion? It's circular. What is the property of this motion? It's parabolic, and we will learn it later. But at least it's not circular. So language is the fundamentally important thing. You have to memorize a lot just to learn that language. And of course, for everything in physics, we have something we use to describe those properties in numbers, like mass or weight or temperature, etc., etc. So, and then we need to know how those parameters might be related. Those connections in physics usually based on certain equations. And this is a copy from the syllabus. This is how much stuff, technically, you need to memorize eventually. But if you are a pre-med student, this is nothing relative to the amount of names you have to memorize. You have bonds, muscles, chemical substances, and pills, medicals. So use this as a training for your memorizing skills. Physics is a science. What is a mission of any science? What do you think? You know, if you're a business major, you know every organization has its mission. Science is not an organization, it's a human practice, which has certain organizations. But as a human practice, it has its own mission. What do you think is the mission of science? There is no wrong answer. To understand why do we need that? What for? What do you think?
Applying it to the world.
Applying. How do we apply it specifically? For what? What do you think? What do you think? If you think it's you, it's you. To make improvements. And to make those improvements, we base our actions on what? What every science helps us to do. That's the general. We already passed that. We're making more and more specific statements. There's something very specific which every science helps us to do. And without that, we don't know what's going to happen tomorrow. We don't know what's going to happen in a minute. Predictions. Predictability. That's the mission of every science. And then we use that for everything you said, to make our lives better eventually. And to be able to predict things, first we have to saw something which, well, can be predicted. Something which repeats itself. And that's what we call patterns. So in science, we search for patterns, and then we use those patterns to make predictions. And to search for that patterns, we need data. So if something is not based on data, it's not science. And why mathematics is an important part of this? Well, because in physics, patterns are not just like that. Yeah. In the real world, we have many, many patterns. There are audio patterns, visual patterns, numerical patterns. But in physics, we have specific patterns. We call them definitions or laws. And there's a big difference between these two. So I'm going to give you 30 seconds to think. What do you think a definition is? And now I'm going to ask this question to the person who's the farthest from the bench. What is a definition? How would you define a definition? What do you think is a definition of a definition? Anything goes.
What something means.
What a word means. Okay. But what if you mean one thing and another person means another thing? Would it be a definition? Well, I'm not going to spend too much time on it. You can read it online, of course. A definition is not just what something means, but a definition is when everybody agrees on that meaning. So someone said, okay, let's call it speed. And if everybody agreed, that's it. It becomes a definition. And for that, what we call speed now, people used to have many, many definitions, but only those which used to be more convenient, more valuable, yeah, practical, survived. And what is a law? A law is not based on agreement. A law is that relationship which doesn't depend on anybody. It's a relationship which has been extracted from experiments, from analyzing data, and turns out that this thing is related to this thing, no matter who and where and how it measures. So when we start to study something in physics, we have to learn definitions word by word. We cannot give our interpretation because people didn't agree on our interpretation. So we have to agree with those people. Same with laws. If there's a law, there's a statement, usually a word statement, textual statement, and an equation, a mathematical statement. And again, we just have to follow literally those statements. And we're going to be all set. And of course, because we people know algebra, we can combine certain definitions and laws together, and we can derive some other equations which not fundamental anymore, but still might be convenient to memorize just for the sake of saving time. Instead of deriving the same again and again and again, you just know and use it. And physics, naturally, for me, is the most important subject in the world. But also, if you look at many current human practices, they're more and more based on applications from physics. And when I moved from Russia, I was really surprised that high school students here don't really learn physics. You know, when I was a student, when my son was a student, everyone, every single high school and actually middle school student had to learn physics. More or less, you know, but still. And I think that one of the reasons why Russian FSB beat US FBI in 2016. They've been just a little bit smarter on things because of physics, not because of me. I have nothing to do to that. Well, these week's topics, we're going to talk about, well, we have talked about physics extensively already. So we're going to talk about motion, one-dimensional motion, two-dimensional motion, and this is what we're going to learn in 2 weeks. These are topics for the upcoming exam number 1, and you will learn it. I know it. Physics, of course, uses mathematics. So when we describe things using words, we use language. When we describe things using equations, we use mathematics. So we need a bridge between these two ways of describing nature. And in physics, well, in any science, this bridge is measurement. Well, this is a standard measurement you can find in Wikipedia, for example. We don't use it in physics. It's too broad. We use a more specific version of it. This is what we call measurement in physics. To measure something in physics means to compare a certain property of a certain object or a process with the property of an object of a process we named a standard. And historically, physicists have developed many different standards. All the most convenient, again, survived. For example, most convenient system of units right now, system of standards, is based on measuring time, measuring mass, and measuring distance. So mechanics is all based on just measuring these three parameters, characteristics. Time. Well, I need my time machine. Got it. So again, first we need, well, why do we call it a standard? Because something standard is happening to it again and again and again. So if we want to measure time, we need to find a process which consistently repeats itself. It could have been the time for the Earth to make one whole revolution about the sun. Or it could have been a time for this ball to make one whole swing. So we choose, we agree, and then we have to call it. Let's call it a year, or let's call it a second. And then we just need to be able to count how many these units, seconds or years, we can fit in a certain time interval. For example, I can count 1 Mississippi, 2 Mississippi, 3 Mississippi. So it took 3 seconds. But of course, right now, we don't use this. We use better devices, like watches or anything else. They all calibrated toward the same standard. So nowadays, it doesn't matter how we use time, because they're all consistent. Same with length. So we could have used this length as a standard. What's wrong with this? Well, if everybody would need to use it, you would have to cut it and take it away with you. So instead, what people did, well, they used a rod made of platinum gold alloy, and they called it a meter. And then they took a piece of wood and cut exactly the same, length. So this is 1 meter, and it's much easier, now to cut more and more like this and use it everywhere. So if I want to measure now the length of something, all I need to count is how many of these standards I can fit in it. 1, 2, 3. So 3 meters. And of course, I can use parts of it, decimeters, millimeters. What about mass? Well, same thing. Unfortunately, this is not gold. Otherwise, probably I wouldn't be teaching anymore. Or I would be teaching somewhere else. Not in Russia. I like Switzerland. So, not gold, but as heavy as this. How do I know? Well, of course, I can't use that one. I can't steal it. It's heavily guarded. But what people have done in the past? Well, this is how I could use my hands. I guess this is not heavy enough. If I take 2, good, yeah. Same feeling. So if this is 1 kilogram, these 2 also 1 kilogram, or which means this each is a half of it, but that's not very accurate. So we use devices like a spring, right? We can attach and see how long this spring becomes. Then we can attach these 2 and see that its elongation is exactly the same. We make conclusion, same mass. And of course, based on this, we've developed many, many different devices, electronic devices, string devices. All we need to know is how to press a button. If it's calibrated, it will give you the right number. And, well, this is actually 1011 grams. So it's roughly 1,000 grams, which is 1 kilogram. So when we have established all standards, we can use them to measure things differently and then make a correlation, or we call it conversion. 1 meter, this is 1 meter. If we divide it into 100 equal portions, that small portion has a name, a centimeter. And this is a mathematical relationship which says 1 meter fits exactly 100 centimeters. Every relationship like this has a name, a conversion factor. And there are hundreds of those. These are just examples. So every time when you need a conversion factor, you can just find it in a textbook or Google it. Well, let's see if this works. 54 miles per hour. That's, for example, the reading on your speedometer when you drive. What is in meters per second? Well, see, we have to make two conversions. We have to make a transition from miles to meters, and we have to make a transition from hours to seconds, which means we need two independent conversion factors. Okay, so what do? We search miles. 1 mile equals 1,600 meters. How do I know? I can read. Now, 1 hour is equal to 3,600 seconds. So what do? Well, technically, this is what we need to do. That's 54, and here there's always an invisible one, 1 mile, and 1 hour. And now we enact a procedure which in mathematics has a name, a substitution. We keep 54. We do not change this number, but we can replace 1 mile with a number which is equivalent to it mathematically. 1 mile, okay. 1,600 meters. And we can substitute, which means replace 1 hour with 3,600 seconds. Now it's time to take a calculator. So these variables, they called units of measurement, represent what should be used to measure this number. Meters for length, seconds for time. And this number is just now a result of a calculation. And to do that calculation, you need a special device. You don't need a graphic calculator. You don't have to. A regular calculator usually is sufficient for all your work. Or you can even, for your homework, you can use a smartphone, but you need an app with sine, cosine, tangents, squares. So here, what do we have? 54 times 16 divided by 36. Well, in my mind, I cancel these zeros, right? Because I always can. Equals, I got 24. Sometimes I make mistakes, but it's not my fault. My calculator makes mistakes. But in this situation, my calculator did the right job. So this is just a standard example of converting units. And now you're ready to finish your first homework problem on a web assignment. The waterfall is 104,851 deep. Please tell me, anybody. Exactly. What is it? Seconds, miles, apples. So when you finish your work and you write a number, you have to write the correct unit. in physics, we have certain exceptions. Very few physical quantities which are unitless, don't have any, but it's very rare. So in this situation, that should be millimeters. And what do? We have no intuition on millimeters. Well, you can convert it. 104,851 millimeters. Actually, it's about 333 feet, or about 100 meters. Any questions? Well, sometimes we don't really care. Do we need to use meters or miles or centimeters for something? Those units which we can use to measure the same physical quantity, they form so-called dimension. So there's a dimension of length. That includes meters, centimeters, millimeters, miles. There's a dimension of time. That includes seconds, hours, minutes, years. There's a dimension of mass. That includes grams, kilograms, pounds, tons. And this symbol, brackets, represent this word, a dimension. So for example, a dimension of variable A. Why is it important? If we compare a dimension of an equation on both sides and they disagree, this equation is wrong. It's just plain wrong. It's impossible in physics to have a correct equation when two sides have different dimensions. If they have the same dimension, it doesn't mean it is correct automatically, yeah, because it doesn't say anything about coefficients and numbers, but at least it is possible. Here, an example. We know that the dimension of mass is mass. And as soon as I wrote it, I can point at very, very common situation, which happens in physics all the time. Very often, we use exactly the same letter for completely different things. It's because the alphabet has only 26. British alphabet has only 26 letters. Even Greek alphabet has, I think, like 28. So, but we have many, many more physical quantities. So every time when we write a variable, every time when we write a letter, we have to be able to say out loud its exact meaning here and now. Yeah. So here is some physical mass of something, and here m is the unit. Speed. Well, for the speed, we can use an equation which we will learn tomorrow. Again, because everybody knows it. Distance over time. So for the dimension of speed, dimension of the speed is equal to the dimension of some length over the dimension of time. Now, a standard letter for a dimension of distance is a capital L, length. But a standard letter for a dimension of time is a capital T. So again, there is no confusion between S and L. That's a specific distance. This is the dimension of that, what we use to measure unit of distance. This is some kind of a specific time, and this is a unit of time. Might be seconds, might be hours. And what do we know? What do we do now is just plug it together. mv squared over 2. So we break it down. mv squared over 2. What is the dimension of a 2? Does it have any unit? No, it's a coefficient, like a pi, number pi, or any other number. So it has no dimension, and it means we don't write any letter. But we can't just leave it empty space. So we have to write something. We have to write something which doesn't affect mathematical meaning of this. So what should we write? What do you think should we write here? What number doesn't affect? 1, yeah. No dimension means the dimension of this, the unit of this is 1. And we write m, and we write L squared over T squared. And now it's a pure algebra. M over 1 is m, still m. L squared, T squared. This is a unit or a dimension of that physical quantity we call kinetic energy. So if we use meters, seconds, and kilograms, in that situation, we would measure kilogram, some number, kilogram, meter squared over second squared. However, we could have used pounds or grams, centimeters, and years. And in that case, the same quantity would have a different units, but of course, it would have a different number as well. Well, and of course, you can Google and find dimensions for all important physical quantities. And of course, if you have any question about anything, you can ask. I'm not going to ask this question today because we are almost done. I don't want to waste our time. The answer is no. How do I know this? Well, this is how. On the left, we have a variable which should be measured in length. Maybe meters, maybe miles, doesn't matter. What do we have on the right? A half is the coefficient, has no dimension, so 1. And invisible or visible, doesn't matter. Speed, we just know it has dimension length over time. Time squared, so we can cancel 1t. Now we do algebra. 1t cancels here. So what's left on the left? Length. On the right, length times time. That is impossible. So this equation just cannot be correct. If you did some mathematics and you arrived at this equation and you checked, you should say, I made a mistake somewhere, because that can't work. That's why the dimensional analysis might be helpful. This is what I want to ask you. So that's the question number 5, not 4. You skip question 4. You go directly to question 5. This object has a name. We call it a cube. So this particular cube is 10 centimeters long, 10 centimeters wide, 10 centimeters high. So we can calculate the volume of this object. To calculate the volume, we have to multiply 3 numbers. The result has a name, 1 liter. That's exactly what we call a liter. It's like this. If you have a 2-liter bottle of Pepsi, it has 2 cubes like that inside it. But we need to be able to convert it into units we use, standard units we use in physics. So in physics, we should have used meters, meters, and meters. A meter times a meter times a meter should give you a meter cubed. So in physics, to measure volume, we would use 1 cubic meter. And literally, 1 liter is much smaller than that. So the question here is, if you would use international system of units, what answer would you choose for 1 liter from this list? And I didn't have to say anything. It's self-explanatory. I just had to spend some time to give you, an opportunity to enter your answer. And again, remember, that the question number 5 All right. So, well, right now I have to make you feel sad. I have to. Because as I said, out loud, to measure volume using International System of Units, we have to use what? Meters cubed. Do you see anywhere cubic meter? No? So, next time pay more attention to details, right? So, but if we want to do a number, what would we do? It's very simple conversion problem. So, the volume, which is 1 liter, literally is a product of this 10 centimeters times 10 centimeters times 10 centimeters, but it's in centimeters. We actually can combine tens and centimeters together. And we can see again, we have length cubed. What do we need to do now is what? We have to use a conversion factor. A relationship between a meter and a centimeter. That was on one of the previous slides. 1 meter is equal to 100 centimeters. It's a given conversion factor, but we cannot use this one directly. First, what we need is reverse it. 1 centimeter will be equal to what? One hundredth of a meter, or if it's a simple number, we can use a decimal point. Or if we are proficient with scientific notation, we can use an exponent. No matter what we use, the result is this. So we need to replace a centimeter with its value in meters. But what people usually forget, it's cubed. So the result is 10 to the third times 10 to the, well, 2 times 3, 6, negative 6. So 10 to the negative third, or 1/1000th of cubic meter. That's 1 liter. And again, visualize it. This is 1 cubic meter. And this is 1 liter. So how many small liters can we fit in it? 1,000. That's why the volume of 1 small liter is 1/1000th of a cubic meter. Any questions? Last note, very often we need to use a scientific notation, powers of 10. And in physics, for every important power of 10, we have a name. 10 to the 9th, billions. 10 to the 3rd, thousandths. And we call them kilo, giga, deca, hecta, milli, micro, nano, pico. And that's my cue. We are done for today. Well, technically, we still have 1 more minute, but you're free to go.